So what have we been working on? We've spent, I guess, already this whole week working on elementary number theory. But we are all done with that now, and today we are starting a new topic, which is induction. So, what is induction? So it is a new proof technique for situations where you want to prove a statement, something along the lines of some proposition for all natural numbers, or positive integers, or something like this. We'll see a couple of variations and what kind of situation it applies when we start doing examples. But let's do a little bit of high-level discussion first. So, principle of mathematical induction. What is this? So, let P of n be a propositional function where n takes natural number values. And how induction works is if you know that P of 0 is true, and also you know that P of k implies P of k plus 1, then you know it's true all the time. The n is true for all n natural numbers. So this is basically saying, you can almost think of it as an axiom about the natural numbers. It's saying that starting from 0, you can make every natural number by a finite number of steps adding 1. And so if you want to prove something for every natural number, it suffices to prove it for the first one, and then to prove that you can get from each one to the next. So this is called, this part is called the base case. And this is called the induction step. And people often like to give analogies for this, like you're climbing a ladder or climbing a staircase or something like this. So, for example, what does it take to climb a staircase of any height? You basically need to be able to do two things, which are, first of all, you need to be able to find your way to the bottom of the staircase. And second of all, you need to know how to go up one step. And if you know those two things, then you can climb any staircase by first getting in position at the bottom, and then taking a step, and continuing to take steps until you get to the top. So let me say one more thing about this, or just kind of go over again how you would do this proof. So for the base case, you prove P of 0 directly, or however you want. And then in the induction step, you assume that P of k is true. And this is called the induction hypothesis. So basically it's the hypothesis that we're making in order to perform the induction step. So assuming the induction hypothesis, you assume this is true, and you prove that P of k plus 1 is true. And you may see many variations, simple variations in the sense of like pk minus 1 implies pk or something, different letters. So let's look at a simple example. So this. So let's try and prove this formula. The sum of the first n squares is equal to n times n plus 1 times 2n plus 1 divided by 6. So we have this nice formula for the sum of the first n squares, and we will prove it by induction on n. So what we're saying here is that this statement is what we're calling P of n, and we will induct on n to prove this result. So what is our base case? Well, maybe I should specify this in the claim. We're claiming this is true for n greater than or equal to 1. So again, there's a lot of small variations you'll see. The base case is going to be whatever case you're starting from. So it might not always be called 0, might not always be called 1. It could be 2 or 3 or 4 or something else entirely. But the base case is wherever you are starting. So here, we're starting from 1. So let's take the base case to be n equal 1. Then our equation is 1 squared. Let me use this question mark to mean that I'm going to write down this equation without knowing that it's true yet. So this should be 1 times 1 plus 1 times 2 times 1 plus 1 divided by 6. So then this side is 1, and this side is 1 times 2 times 3 divided by 6. That is 6. 6 over 6, right? So this is 1. And they are indeed equal. So that's the base case done. Now the induction step. Let's, so in the induction step, we make our induction hypothesis, and then we prove the next case. So our induction hypothesis is assume the statement is true for, how do I want to do it here? I think I want to say it's true for n and prove n plus 1. So assume it's true for n, which is to say that 1 squared plus 2 squared up to n squared is equal to n plus 1, 2n plus 1 over 6. And let's also write down clearly what we want to prove. And we want to prove that, so basically we replace n with n plus 1 everywhere on both sides. So 1 squared plus 2 squared plus n squared. Now we're working up to n plus 1 squared should be equal to this formula, same formula, where we have replaced n with n plus 1. So n plus 1 times n plus 1 plus 1 is n plus 2, and 2n plus 1 is 2 becomes 2n plus 2 plus 1. So this is the computation that we're doing. So this is 2n plus 3 divided by 6. So I'm going to use this question mark just so I can work with both sides of the equation at the same time. And then if I find at the end that they're the same, then we'll be good to go. So this is what we want to prove. And how are we going to prove it? Well, of course, we're going to use our induction hypothesis. So let me call it, let me write that down. This is our induction hypothesis. And how are we going to use it? Well, we have something that's looking very ripe for a substitution. So let's make that substitution and see what we get. So we're using the induction hypothesis here to rewrite this as replacing this with this. So n plus 1, 2n plus 1 over 6 plus n plus 1 squared. Is this equal to n plus 1, n plus 2, 2n plus 3 over 6. And let's look at what this has done for us. So before, we had this expression where we had some arbitrary number of terms, so it's hard to work with it concretely. We can't just write down what that is. But now, over here and over here, on both sides, we just have some concrete thing that we can just write it down and see if they're equal. So that's all we have to do. So let's do it. I'm going to multiply both sides by 6, just to make the numbers easier to work with. So we get n plus 1, 2n plus 1 plus 6, n plus 1 squared. Is this equal to n plus 1, n plus 2, 2n plus 3? And then, okay, let's try to blaze through this a little bit, because from now on we're just going to be expanding, just foiling, a lot of foiling. You know, I hope you're familiar with foiling. Got to know your basic pre-algebra. So this becomes 2n cubed. So let me do this first and then just raise the powers by n. So this is 2n squared from that term, and then 3n from those terms, plus 1. So it's 2n cubed plus 3n squared plus n. And then this becomes n squared plus 2n plus 1. And then you multiply that all by 6. You get 6n squared plus 12n plus 6. And on this side, let's do this first. We get n squared plus 3n plus 2. And then if we multiply that by this, we will get 2n cubed plus, let's just do each term by itself. So 2n cubed plus 6n squared plus 6, and then 3n cubed, 3n squared, rather, plus 9n plus 6. And now if we collect terms, 2n cubed plus 9n squared plus 13n plus 6 is equal to 2n cubed plus 9n squared plus, I think I'm missing an n here. I think it should be a 4. So I got this. Oh, excuse my arithmetic errors. I got this by multiplying this and that. So it should be 4n. So now our math is working out. We are getting 13n plus 6. And we see that they are indeed equal, which completes the induction step. So now let's just account for what we've done. We wanted to prove this formula. Let me wait for my screen to catch up real fast. We wanted to prove this formula at the top. And how did we do it? We proved the base case in the case that n equals 1. And then we proved that if the formula holds for n, then the formula holds for n equals for n plus 1. And proving that was just this algebraic computation. And now, having proven both of those things, the result follows by induction. So let's write that. So this completes the induction step. And the result follows by induction. So there is our first example of a proof by induction.